band, The Sound of Science.
Speed of light, of light. Speed of light, of light. Light takes 500 seconds. Travel from the sun to the earth. Light takes 1.3 seconds. Travel from the moon to the earth. And light takes almost 4 hours to journey from Neptune through space to the earth. Speed of light, of light. Speed of light, of light. Light takes 4.2 years to travel from Proxima Centauri to the Earth. Proxima Centauri is the closest star to our sun.
2.5 million years to journey from Andromeda Galaxy to the Earth.
Speed of light, of light. Speed of light, of
Kilometers per hour.
Welcome to the stage, Nate Adams and Duncan Cameron.
Hello! How is everyone? That was appalling. Hello!
Hello!
That's much better. Hello, welcome to the University of Sheffield and welcome to Festival of the Mind. Can we have a massive round of applause for our band? What university does this?
Yeah.
Is that all right round of applause? Is that okay?
So I would like to remind you, it is Saturday morning, you're not at school, you're not at work, and you have happened to find yourself at a science concert.
I think we just need to make sure that we're all calibrated so we know how to respond appropriately to what you're going to see tonight. Okay, so if you see something that's mildly amusing, vaguely tickles your fancy, you might want to give it a gentle round of applause. A gentle round of applause, everyone. Keep going. And then maybe if it gets a little bit better, maybe it's like, oh, that's a big fire. Maybe you want to go, yeah, I quite like that, quite like that. And then if the band does some amazing tune, you want to go, whoa! Yeah! And if at the end, and I don't kill you all in the final explosion, go crazy! Yeah! Woo! Perfect. And now you know how to protect our fragile egos. Very much appreciate it. So welcome again. This is Festival of the Mind. This is where the university allows us to go slightly OTT. And we're doing this.
OTT, Nate, really?
No, never. And we're doing it inside of our grandest of halls, Firth Hall, named after our founding benefactor.
So if you look around you, the walls are filled with portraits of some amazing people. And these people, they've used their voices to make a change in the world. And today, we're going to use our voices to tell you a story about science and how science at Sheffield is changing the world and making it a better place for us all to live.
So we started off with a song about the fastest thing in the universe, light. Now this is part of something called the electromagnetic spectrum, and I love light. But for me to tell you more about it, I need to bring on our amazing mobile laboratory. Give a round of applause to the mobile lab and Melanie Hannah, who has helped us design all of the demonstrations for tonight. So light, it's this ridiculous phenomenon. It barely exists physically, but illuminates everything around us. And scientists use light to investigate how the universe actually works. But what's even more interesting about light is that it developed pretty much with humanity. So as humans worked out how to use light, capture it, they also evolved into the species that we are today. So I thought I'd go through some of that history now. So when humans first came down from the trees, as it were, they first encountered fire, not that easily, but it was more from forest fires, lightning striking grass plains. And they went, that's a very interesting thing. And they worked out how to make it themselves by rubbing two sticks together. That would create friction, and enough friction creates enough heat, and then you get fire. But I'm a terrible Boy Scout. And no matter how many times I try and do that experiment, it fails miserably. So instead I thought I'd play to my skills, which is chemistry. Now, I learned in university that if you compress a gas fast enough, it will get hot enough to actually set things on fire. So I've got a bit of cotton here. This is a flammable material. I'm going to place it inside of my piston like so. And then I'm going to seal it in there. And then hopefully, if I compress the air fast enough, according to science, it should get hot enough to set that cotton on fire. Should we see what happens? Yeah, all right. Yeah. Getting there. We'll get better. Right, so here we go. In 3, 2, 1. Yes! It works! Woo! Mild titter of applause. Excellent! You know what we're doing. So yes, we can set things on fire, and as soon as we worked out how to make fire, that changed everything. We could start to cook food. And when we cook food, that starts breaking down the food and allows the nutrients to be released, which then we can absorb and actually made us smarter. Now, with these newfound smarts, we didn't rest on our laurels. We did what any good university student would do. They did research. They worked out that we needed to have a better way of transporting light. And they started off by using fat, animal fat. Now, I'm a millennial. I do not know how to butcher a cow. But I do know how to go to Sainsbury's and buy a block of lard, which I melted and put inside of a seashell to mimic an early human lamp. This is a scallop shell that I got from the raw market. And lard is actually surprisingly flammable. Who would have thought? That's because lard is fat, and fat is an amazing energy source. We'll just get that candle lit over there as well. And so as the lard melts, it then gets melted even more and gets converted into a gas. That gas gets so hot that it starts reacting in the oxygen around us, and mainly it releases energy as heat. But actually a byproduct is we get a bit of light as well. Now, we also worked out that we could make lamps using oil, but fundamentally the most important light source that we've had for thousands and thousands of years is the humble candle. Now, this fuel source here has democratized light. It allowed many, many people to see. It allowed people to stay up late into the night and were able to work and then research and do further things. It led to the Age of Enlightenment, the Renaissance, all these things that developed us as a species. But that's where things stayed for quite some time. Until scientists and alchemists started playing with electricity. But even then, things took a while to progress forward, until Thomas Edison patented his famous light bulb. Now, you might remember the old-fashioned light bulbs. They had a filament of wire running through them, just like this wire here. And if you pass electricity through wire, it will actually start to glow. So much heat is formed that we get so much heat, we get black body radiation, and light starts to happen like we're seeing here. That's just wire wool there. So now you've learned not to store your wire wool anywhere near your car batteries in the garage. So we had that, and we had incandescent light bulbs for a very long time, but they're incredibly energy inefficient. They lose so much of their energy as heat that human beings, we worked out we need to be better to help make the planet a more sustainable place. So we started creating energy-efficient light bulbs, such as these, fluorescent tubes. Now, you still see them. There's some outside here. They're still used in offices and shops. And these fluorescent tubes are filled with a mercury gas. And when you excite that gas with electricity, it glows and then produces a nice white light. But I'm not going to use electricity. I'm going to use my favorite scientific toy, the plasma ball. So let's just turn that on, and we'll have the lights come down. I love plasma balls. It was my first scientific toy that I had. It's so gorgeous. Look at that. So you've got a very high voltage exciting a gas inside here producing light. But what you might not know is that the electrical power is emanating even further. There is an electrical wind coming out of that plasma ball. So if I take the fluorescent tube closer to it, we should see something amazing. Whoa, yeah. I love this demonstration. So the electrical wind is actually so powerful that it's able to excite those mercury atoms inside of there. I think it's so beautiful. And that's one way of energy efficient lighting. But as we got better and as we moved into the technological age, we've moved forward to using LEDs. So these panels here, these are all made with LEDs just here. These LEDs here. Actually, everything on stage is LEDs pretty much. They're very, very energy efficient. So energy efficient, in fact, we can put them into clothing, which I do believe our professor will be demonstrating now. Here's some of my fabulous LED wear that I make at home.
You are in a whole world of trouble. You understand that?
You look gorgeous.
Career over.
I don't
I always
understand
look gorgeous.
what you're complaining about. So LEDs use a combination of chemistry to be able to produce loads of different colors. So we can see Duncan's got all the different colors of the rainbow being demonstrated there. So we can see that we can create light using a combination of converting energy via different ways, either by fire, electricity, electrical wind, and then we can create different colors using chemistry. So I thought I'd combine them together to do my favorite thing, which is to make a flame bow. So bring on the flame bow! Here it comes, everyone. This is my new demonstration, which we're still perfecting, I'm not going to lie, but it works 50% of the time. Now what I've done here is I've got a whole load of water cooler bottles. I filled them with a flammable gas, and I've also filled them with different chemical elements. So elements such as strontium, lithium, calcium, copper, potassium, and sodium. And then I've got electrolytic matches in them so I don't burn myself and end up in hospital again, like the last time. True story. So I've got my own detonator igniter that I built here. Small child there, please don't run up and attack. So I think we should see what it looks like.
Hang on. Before you do this, he's got quite a big ego, so I think he deserves at least a little countdown, okay? So shall we start at 3?
I think 3's all right.
All right, you okay with 3? 3, 2, 1, go!
Woo! Just keep going, it just keeps going!
Now, what's amazing about the flame bow is the different colors that are generated come from metals. And I think one of the most amazing facts about these metals is that lithium that created that beautiful pink glow actually was created at the very dawn of the universe. It was created in the Big Bang, even before we had stars. I think that's absolutely amazing. But why should we care about light? Obviously, it's really important. That's how we see around. But the reason that every living thing exists on planet Earth is because of light. And that's because of the beautiful dance that occurs between plants and light that is called photosynthesis.
Plants grow from seeds. Water, sunlight, CO2. The oxygen we breathe comes from plants on land and seeds.
the green machines.
Photosynthesis. Love the green machines.
Love the green machines. Photosynthesis.
Love the green machines.
So cool having a band. So, light from our local star, the sun, provides all the energy to the plants, which then grow all the food that we eat, which means we eat sunshine.
Yeah, absolutely. We all eat sunshine. And I think that's amazing. But we do know that not everybody on the planet has enough food to eat. There are about 7 billion people living on planet Earth today. And by 2020, we think there'll be 10 billion people. So we can't feed 7 billion people now, but we need to feed 10 billion people by 2020. How on earth are we going to do it? And photosynthesis might be one of the answers. Now, if you look at the screen behind me now, you can see photosynthesis happening. This is a pondweed, and we can see little bubbles of gas being produced. And those little bubbles of gas are the waste product of photosynthesis. That's oxygen, oxygen that we breathe. And all of the oxygen in our atmosphere comes because of photosynthesis. It's amazing. But if we want to understand how we can make photosynthesis better and help us make more food for the growing population, we need to scale things up just a little bit. Well, quite a lot, actually. And if we're going to do that, we need to use something like this. Meet RoboPlant. I think he deserves a bit of an ooh. Ooh. RoboPlant is kind of what you would expect. It's a robotic plant. Everyone has one. It was invented in Sheffield by my really good friend, Professor Colin Osborne. And he invented it so we could look at some of the first stages of photosynthesis. Now, photosynthesis is amazing. It's lots of different chemical reactions that are all stuck together that take light at one end and create energy that we can use at the other. And the first of those reactions was discovered here in Sheffield in 1937 in this very university by a guy called Robin Hill. And it's now called the Hill reaction. And what the Hill reaction is when light hits a plant, so it hits RoboPlant cells here, and that light then is used to literally tear the water molecule apart. So we know water is made from oxygen and from hydrogen, and the plant is using the light to rip the oxygen from the hydrogen, and the oxygen bubbles into the atmosphere. And the hydrogen is the first step in producing energy that we can use.
Did you just say hydrogen?
Oh, I
Duncan?
know what's going to happen now, and this is not good.
So hydrogen is an amazing element. Within the plant, it provides the force, then starts to actually break down and produce the sugars that we need to eat, and the plant survives on. But if we just extracted that hydrogen just there, we can start doing some quite fun things, because hydrogen gas it's exceedingly flammable, shall we say. And I've got a balloon of it just here. Bring on the lab! Whoa. I know it's just 2 bowls of water. Balloon. But I do have 2 bowls of water here. One of them is everyday normal water. One of them is bubble mix. I've got a balloon full of hydrogen. Bubble mix, balloon, bubble mix. Fire bubbles! So I'm going to pass a few things, and I need to choose someone to set on fire.
Not going to happen. Beard, come on. Extremely flammable.
Bloody hipsters with their beard oil. Guys, anyone? They've all got long sleeves on. I can't set fire. Have we got Amy?
Come on, Amy.
Please come out. Everyone, say hello to Amy. Let's give her a round of applause. Amy's a postdoc here in the Department of Biomedical Sciences, I believe, and she's been thrown at the deep end by doing her first science show with me. Do you mind me setting you on fire?
No, why not?
It's all right. Okay, so I need you to get your hands nice and wet there, so you're covered in with a protective layer of water. I'm just going to get some hydrogen. Just going to pass it through and make a few bubbles. A few fire bubbles. Ooh, that's twisted as well. Just There we go. Is that enough bubbles? You happy with that? Okay, we'll do that to begin with. Right, let's see what happens. Right, put the hydrogen down there. So if you can just pick up those bubbles for me, and then got some bubbles. Excellent. I'll just take the bottom off. And then little countdown. So 3, 2, 1. Whoa. I think that deserves a little round of applause. That's too much. That was not big enough. Right, should we do it? Should we go bigger? Yeah. We'll go bigger. Right, because I've got loads of hydrogen left. That's my favorite. Right, let's get a load. Oh, hello. Oh, let's go big. Oh, there's some big bubbles there, Amy. You'll be fine. You're okay. That's quite a few bubbles. Oh, it'll be fine. Here we go. Right, you grab them. I'm just gonna get rid of that. Just make sure you've got. Oh, let's get a load of bubbles. That should be a bit bigger. Right, so countdown again. 3, 2, 1. Whoa! That deserves a big round of applause. And she's not screaming, even better.
So that was quite impressive. But I think I've seen you do an even more impressive experiment with hydrogen.
The thing is, hydrogen is used in rockets as rocket fuel. So obviously I've made some hydrogen rockets to fire at you guys.
Convenient, that.
Here we have a bucket. Inside this bucket, we have a Coke bottle. Other brands of soft drink are available. With some foam on the top, so if it does hit you in the head, it doesn't hurt too much. So I'm just going to empty the water out so we get a nice hydrogen-oxygen mix, like so. Grab my lighter, and then in 3, 2, 1. Woo! Nice catch. No, fail. Boom. I've got another one. It's all right. Let's do it. 3, 2, 1. Woo! These are good today. But hold on. Why did the rocket come back down to Earth?
In the year 1687, Isaac Newton published his book, Principia, which presented his theory of gravity.
If you ever wonder why the moon doesn't float away,
Because the Earth's gravitational pull holds it in place.
why do the earth and moon dance round the sun?
Because the mass of that beautiful star is greater than both of them. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground.
If you ever wonder why the seas rise and fall,
Because the dry and dusty moon is covetous.
why does the apple drop down from the tree?
Because everything on earth is attracted by its gravity. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground. Gravity's the force that keeps your feet on the ground.
In 1915, Albert Einstein published his general theory of relativity. It described gravity not as a force, but as a consequence of the warp of space-time. The warp of space-time.
Einstein said that gravity is the law of space-time. Einstein said that gravity is the law of space-time.
I really love gravity. What with the whole, not flying off the Earth thing, or to be honest, the Earth would never have formed, the solar system wouldn't have happened, the universe as we know it wouldn't exist. So, yes, gravity is very, very important to us. But I also love gravity because it really introduced me to science. It was the first science experiment I ever did in high school was to calculate gravity. So I thought we'd go back in time and recreate that moment right now by doing maths live on stage. Woohoo! You will be more excited in a moment. To do this, we need to have a pendulum. And I thought, what's the best way of doing a pendulum? Well, a giant disco ball. It is pretty giant, actually, to be honest. You did well. But I just think because of what's going to happen to Duncan's face, we might have to go for something slightly... we talked about it before.
No.
Be right. I do think we've got something back here. Where is it? Hold on. Here we go. Oh, hello. It's all sliding all over the place. Sorry, Sharon. This is my disco ball pendulum gravity calculator-tron.
We spoke about this.
It's very pretty, isn't it?
Your career is definitely over now.
It's all right. So, to be able to calculate gravity, I just need to get my notepad out. And we need a formula that's going to appear any moment. Hey, we've got a formula. Everyone loves 4 pi squared times the length of the pendulum divided by time squared, right? Yeah? So, Duncan, could you please calculate the length, measure the length of a pendulum?
I conveniently have a tape measure in my pocket at all times.
Let me just get my pen out.
The pendulum is precisely 1.13 meters.
Well, okay, so it's 1.13 meters, all right. So next thing we need to do is measure the time of the oscillation. I'm just going to pass that to Mel, and I am going to do it in my head, everyone. So an oscillation is the period of time it takes to go from here, back, and then here again, okay? So that's one oscillation. Now we need to do 10 of those oscillations. And so watching a pendulum go back and forth 10 times, it's a bit dull, so I thought we'd recreate the classic physics trick, where Duncan will be sat on this stool. Thanks, Kev. Sat on this stool. And he's going to draw the pendulum to his chin, and hopefully, if it all goes to plan, you won't get hurt. All right? All right. We do need to measure the time of this, so I'm just going to grab a stopwatch out.
You do know my mum's in the audience.
Hi!
And she will do you serious damage if this smashes me in the face.
She said it was fine. So I'm just getting a stopwatch out. Here we go. So we're ready. 3, 2, 1, go! 1, 2... 3, come along.
4, 5, 6, 7, 8, 9, 10. And my beautiful
Right,
face
so
survived.
just so I'm not lying, it says 20.72 seconds. So if we divide that by 10, that is equal to 2. So from that formula up there, times squared, so that's 2 squared. Now, 4 times pi squared is about 38-ish, and then times that by the length of 1.13.
1.13.
That is 44.6. So 44.6 divided by 4 is about 11 meters per second.
He can have a little round of applause for doing that in his head, I think.
I don't even have my iPad.
He'd get a big round of applause if he actually got it right, though.
Oh, come on. Right, so the actual value is 9.81. But considering we did it with the disco ball on a pendulum, that's not too bad.
That's okay.
That's very good. Oh, please you liked it.
So gravity's clearly important. It means we don't fly off into space. But everything experiences gravity, and gravity is really important for the living things around us. And that includes plants. So plants need to know which way's up and which way's down so they can put their shoots in the air and they know where to put their roots. So if you look at the screen behind me now, you should see some roots growing. And they know to grow down. And that's because roots are actually gravity sensors. And it's really important that they know where the soil is, because the soil contains the water that they need to use for photosynthesis, but it also contains the mineral nutrients that are essential for plant growth. And those mineral nutrients exist in the soil as atoms.
Everything's made of atoms, including you and me. The was about tattoos. Is the 99.9% empty space?
So we all need atoms. And nutrients are really important for plants to make things like their roots, their shoots, but also the green color chlorophyll that they use for photosynthesis. And one of the most important of those atoms, of those nutrients, is the element phosphorus. Now, phosphorus is not particularly exciting in its raw elemental form, but given the recurring theme of today's show is fire, I thought we should just set some on fire. Would you like to see some phosphorus on fire?
Of course I'd like to see some phosphorus on fire. I don't know what they mean. I mean, obviously, it's the most dangerous demonstration we're going to do today. I've actually placed on my own boiler suit. I feel like I'm part of the band now.
That's why I'm going to run away. 'Cause I'm the professor, so I'm not doing this.
So, I'm going to even lock it down. And yes, bring on the phosphorus! So, this experiment is relatively dangerous. What I'm going to do is I'm just going to put a heat-proof glove on, light me Bunsen burner. It's the hardest bit. Done. And I'm going to start heating this rod up, if I can pick it up. Here we go. Going to be able to do it. There we go. So, now, phosphorus, as you said, in its raw form, isn't particularly exciting. Oh, let's just get this going. Sorry, everyone. It's a bit of practice here. Phosphorus isn't particularly exciting in this form. This is called red phosphorus. But if we actually set it on fire in an oxygen-rich environment, it is beautiful. It should glow very, very prettily. But when it does that, it produces quite a toxic gas called tetraphosphodeca oxide. Now, if you breathe in that gas, it can cause some pretty nasty side effects, such as diarrhea, explosively, vomiting, projectilely. It makes your eyelids pop inside out and then does some other pretty horrible things to you as well. So that's why we're doing it inside of a vessel. And then if any excess gas pressure builds up, it goes straight into water, which it then actually reacts with instantaneously to produce a harmless acid. So I hope that this is now hot enough to be able to light. We'll see what happens. It looks pretty hot. And then I'm just going to do that. Place it like this, and then, oh, pick it up. Let's go, go, go. And there we go, ladies and gentlemen. Just release that so we get the pressure out. And that, ladies and gentlemen, is the famous phosphorus sun demonstration. Really is rather beautiful.
It's pretty impressive, Nate. Thank you so much for the gratuitous fire. So phosphorus is really important. But we have a problem with phosphorus because we're actually running out of it. So if we keep using phosphorus and wasting it in fertilizers and inefficiently using it in agriculture, we're going to run out of phosphorus in about 100 years' time. So we really need to develop new technologies to allow plants to use less phosphorus in agriculture. Now, the other really important nutrient that plants use is nitrogen. It's really important for all of us. And as you know, the gas around you, the air around you, is full of nitrogen. It's the most common gas in our atmosphere. But most plants, and we, cannot use the nitrogen in the atmosphere. Instead, it has to be turned into a form that plants can take up through their roots. And one of the most spectacular ways that nature can do this is with the power of lightning. I love that bit. It makes me feel very powerful. But what lightning is doing is literally ripping the nitrogen atoms apart in the atmosphere. And when they do that, they react with the oxygen molecules in the atmosphere to form nitrate, which is a fertilizer. And that then dissolves in rainwater, falls to earth, and plants can take it up through their roots. There are lots of ways that we can turn gaseous nitrogen into fertilizer. But one of the ways that humans have evolved to do it is to use something called the Haber-Bosch process. Now, the Haber-Bosch process was invented to create fertilizer for modern agriculture. But as you saw, that process takes a lot of energy. Now, in the Haber-Bosch process that humans have invented, we take that energy from fossil fuels. And of course, we know that when we burn fossil fuels, we release lots of CO2 into the atmosphere. That CO2 accumulates, and that carbon dioxide then traps the heat of the sun and it causes one of the most dangerous phenomena on the planet to humans today, and that is global warming.
Everything you wanted to know about global warming, but were too afraid to ask.
What is global warming?
In the last 50 years, the average temperature of our planet has increased at the fastest rate in recorded history. According to NASA, 16 of the 17 warmest years in the 136-year record have all occurred since 2001. Scientists believe that global temperatures will continue to rise for decades to come because of the greenhouse gases produced by human activities.
What creates global warming?
Global warming happens because carbon dioxide and other greenhouse gases collect in the atmosphere. Normally, sunlight and solar radiation would bounce off the Earth's surface and escape into space. But the greenhouse gases stop them from escaping and act like a blanket, causing the planet to get hotter and hotter.
What makes greenhouse gases?
Greenhouse gases are made by the burning of fossil fuels. Coal and gas is burned in our power stations to make electricity. Petrol and diesel are used in our cars, trains, ships and planes, and factories burn fossil fuels for energy.
What are the effects of global warming?
If we don't change the way we make our energy, then the effects of global warming will become more extreme. Longer heat waves, longer droughts, and more hurricanes. The polar ice caps are melting. Antarctica has lost over 100 billion tons of ice per year since 2002. This could increase and cause sea levels to rise and widespread flooding. We must cut down our CO2 emissions, stop burning fossil fuels. We must take care of the trees and plants which absorb carbon dioxide. We must plant new trees and stop deforestation. We need to use more renewable forms of energy such as wind power, solar power, hydropower, geothermal power, biofuels and biomass.
I'm not going to lie, that's one of the more depressing moments in the show. But it's important to remember that at universities across the nation, across the world, and especially at the University of Sheffield, a lot of scientists are working towards understanding how to make the world a more sustainable place.
That's right. We've talked about how we're investigating photosynthesis, how to make it more efficient so we can make more food, and how we can make crops more efficient at taking nutrients up from the soils so we can spend less energy creating fertilizers and to preserve the nutrient atoms in our soils. But we can't do this on our own. What we need is you. And if you believe that we need to live a more sustainable life, that we need to invest in sustainable technologies, then we need your help. We need you to share our story, talk to your friends, your family, your community, and tell them that things need to change. We need to improve the state of the world, because together we can produce enough food on this planet without destroying the earth.
Whoa! All got a little bit serious.
Dude,
just
I'm a
then,
professor. I am supposed to be serious some of the time.
I know. But, just from a purely scientific point of view, this voice we're talking about, what is it?
I've got an idea.
What makes a sound a sound? So, we've got our most expensive prop of the entire evening here. This is my giant slinky. So, if you imagine in the air, there's loads and loads of molecules, and that's represented by the rings here. When we make a noise, maybe use our voice, or use the speakers, or use the synths, the amazing synths, what's happening is a pressure wave is forming, and that pressure wave transfers down the air, like the pressure waves are going down the slinky, and it hits your eardrum. At that point, it vibrates tiny little bones, which are then creating electrical signals, which are going through your brain to make noise, which I think, well, is interpreted as noise, which I think is amazing.
That is amazing, but I'm sorry. The slinky really doesn't cut it for me. And frankly, you've had all the fun with fire today. I want my turn with fire. So, I have an even better experiment to show you. Now, the wonderful Mel did me a big favor, and she produced a very delicate piece of scientific equipment so I can do an experiment on stage and show you what your voice looks like with, you guessed it, with fire. Now, he doesn't get all the fun. This is something called a Rubens tube. Now, it takes a moment to set up, so I'm going to explain to you how the Rubens tube works. So we have this glass tube here. It's got a stopper at the end, and it's got a load of holes drilled in the top. And at the other end, it's open, but we've glued a speaker to the end of the tube. And what we're going to do is, in a second, we're going to fill this tube with gas. We're going to light it, and we're going to produce a sound from that speaker. And we'll see what happens. So, when we're ready, Let's go. Bit more pressure, I think. Yeah, more pressure.
More pressure!
Ooh.
Hey!
Ooh.
Less pressure!
Slightly less pressure. This beard is going to go otherwise. So this is the Rubens tube. So Nate, do you want to put a tone through the speaker for me, please?
Oh.
So what we should see is the sound is creating a pressure wave in the tube, just like in the slinky. That's bouncing up and down the tube, and it's generating areas of very high pressure and areas of very low pressure. So we have high pressure, we have the big fire, and where we have low pressure, we have the small flames. And this is what we call a standing wave. Now, that's all very good, but it looks a bit cooler if the flames decide to have a bit of a party. So, shall we put some music through it?
I'll just load up the old Spotify.
Other music listening apps are available, of course. And being a product of the 1970s, I kind of thought, you know, a bit of Mario would be a good thing for us to have a look at the flames. Okay. We just have to keep it on fire.
Rubens tubes are really difficult to work with.
They're really,
everyone.
really difficult to work with. This is one of the best demonstrations of it we've had. Excellent. I think we can cut the gas.
Round of applause for
Round
Mel
of
and her
applause for Mel and the
amazing
Rubens
everyone.
tube.
I'm really sorry, Duncan. I mean, the Rubens tube is amazing. It's beautiful. But you're just looking at sound. I want you to feel sound. Do you want to feel sounds? Excellent. So to do this, we need to clear the stage of this dangerous demonstration and get the next dangerous demonstration on instead.
That's not cool. He always has to show me up. He
Yeah,
always has to
sorry,
go
John.
one better.
So one of the best ways of feeling sound is to produce an explosion. I've just got to take that break off. And to do that, we need to, have we got it ready? I'm just going to grab my prop for this demonstration, which is coming. What I need is something that I can create a lot of standing waves in instantaneously to create a large resonance feeling, which of course involves my oil barrel. Everyone has an oil barrel at home, don't they? And inside this oil barrel, I have something that's rather explosive. I have an explosive mix of hydrogen, our old friend from before that was quite flammable, we set Amy on fire with, but also it's been mixed with the correct amount of oxygen to make a really big boom. So when I put it inside of this barrel, that is going to create a whole load of standing waves that are going to vibrate around inside of that, which will then you'll be able to hear. But you won't be able to see the explosion because it's inside of a barrel. But we can show the explosive force by using some ball pit balls. Everyone loves ball pit balls. Let's just get a few more in there. More. You know what? I'm going to make a mess anyway, so if you're around the stage, I aren't going to worry too much. Now, I just need to, there they are there. Grab my ear defenders, because I'm about to make a really big noise. And so before I do that, we need to have a bit of a pre-flight safety briefing. When the countdown begins, I need to make sure that your ears are covered. If you have small people who are unable to cover their ears, please take them out of the room now. Okay? If everyone's all right, we'll go forward. So what I need you to do is to cover your ears, not by sticking your fingers in your ears like this, because you might get a little bit scared. And you might go, ow! So don't do that. Instead, just hands over the top of your ears like so. And that way you will all be safe together. So I'm going to put some ear defenders on because I need to be vaguely concentrating at this. Band, you all right? You okay? You all right with this? Everyone happy? Right. So I'm going to put my ear defenders on like so. I'm going to just grab my detonator. And then should we do a countdown? 3, 2, 1. Yes! That was amazing!
Vibration, 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 vibration,
Frequency.
So that's it for today. Thank you very much. You have just experienced the sound of science.